Okay, everybody, let's look at a theorem that I guess we sort of knew was true. We never actually established it before, but here it is. Suppose that G is an additive group, a finite additive group, and suppose also that the order of an element X is equal to M. Then given a natural number N times the element X equals 0 if and only if M, the order of X, divides N. And let's remember what Nx is. It's X added to itself N times, essentially. So if M is the order of the group, order of the element X, then any other element N, such that Nx equals 0, the identity, is going to be such that M divides or is a factor of N. And let's remind ourselves about the order of an element X. The order of X is M, and M is the smallest natural number, so M can't be 0. M, the order of the element X, is the smallest natural number, or the least natural number, such that Mx equals 0. Okay, let's get into our proof, or at least as much of it as we have on the board now. But we'll suppose that G is a finite group with additive operation, and we'll suppose that N is some natural number, and that the order of the element X of G is M. First, we're going to prove that if Nx equals 0, then M divides or is a factor of N. So we let the hypothesis be given. Nx equals 0. By the division algorithm, there exist integers q and r such that n equals q times m plus r. And remember, the remainder has to be strictly less than the divisor m. So essentially we're dividing n by m, and r is the remainder when we divide n by m. And the remainder has to be strictly less than m, and the remainder has got to be non-negative. The remainder can be 0, or it can be greater than 0, but it has to be strictly less than m. So n equals q times m, where m is the order of the element X, plus r. By our hypothesis, Nx equals 0. And we've also said that n equals qm plus r. So we have Nx equals 0, but Nx is the same as qm plus rx, where r is greater than or equal to 0 and less than m. So what we get from this is that qm plus rx equals 0. So we write that down. And then we distribute these numbers to the element x, qmx plus rx. And then we associate m with the element x first. And son of a gun, what is this? Mx is the identity, right? As a matter of fact, by our hypothesis, m is the smallest natural number, such that m times x is the identity, or 0. So let's continue. This implies Rx equals 0. And we got to be careful here. Remember, m, the order of the element x, is the smallest natural number that we can multiply x by and get 0. And r is a natural number, or r is a number that's smaller than m. It's either a natural number or it's 0. Now, if r is not equal to 0, then that would mean that r is a natural number less than m, and Rx equals 0, the identity. But that can't happen because m, by our hypothesis, is the smallest natural number that we can multiply x by to get 0. So if r is not equal to 0, then essentially that contradicts the hypothesis that m is the smallest natural number, such that smallest natural number that we can multiply x by to get 0. So that means that r has to be 0. So where does that take us? Well, n is equal to qm plus r, but r is 0. And what does that tell us? I think that's pretty significant. Well, let's see. We have an integer times m equals n. So that means that m is a factor of n, or m divides n. Which is exactly what we were trying to show. If nx equals 0, then m divides n. Okay, now we're going to turn it around and go the other way. By the way, I should have put the finishing touches on the first part of the proof and just reiterated what it was that we have shown. And what we had shown is that if n is an integer and nx equals 0, then m, the order of the element x, divides n. Just to restate what it was that we showed. Now we're going to show the converse. If m divides n, and remember, m is the order of the element x. If m divides n, then nx equals 0. So here's our hypothesis. So we let our hypothesis be given. And what that means is m is a factor of n. So there's some other integer, or in this case, a natural number, If m divides n, then there's some other natural number q such that n equals q times m. And let's see what happens when we take x and divide it by n. That's the same thing as multiplying x by qm. And we can associate m with the element x first, so we'll get q times mx. But mx equals 0. M is the order of the element x, so m is the smallest natural number that we can multiply x by and get 0. So that gives us q times the identity, 0, or q times 0, which is 0. So what did we establish? That if m, the order of a group of, if m, the order of the element x, divides n, then that tells us that n times x is 0. Okay, another theorem, or a lemma. We have a group G of finite order, where G equals n, order of G equals n. And what that means is that G has n elements. Then for every element of G, the order of x has to be less than or equal to n. So the order of an element of a group can't be greater than the order of the group itself. So we'll let x be an element of G, and we'll let the order of x be m. And then I'll say, suppose, for the sake of deriving a contradiction, that m is greater than n. And remember what m is, it's the order of the element x. M is the order of the element x. And we're supposing, to get a contradiction, that the order of the element x is greater than n. So somewhere in this proof, we're trying to make the you-know-what hit the fan. So let's see. X is not equal to the identity because the identity has order 1 always. And let's see. If we add x to itself once, And you know what? I guess I don't really need that. If we add x to itself once, we get 2x. If we add x to itself 3 times, we get 3x. And if we add n to itself n times, we get nx. And none of these guys are 0 because we're assuming that the order of x is larger than n. So we have to add x to itself m times to get the identity. Or we have to multiply x by m to get 0, the identity. Which means, since x is the least natural number for this to happen, m is the least natural number such that mx equals 0, that means that all of these other guys they're non-zero. They're not equal to the identity. Well, okay, so far so good, I guess. But this is a proof by contradiction, and the you-know-what is supposed to hit the fan sooner or later. Let's see how that happens. The order of G is n. Then G has n elements. And one of those elements is 0, the identity. But down here, we've got n non-zero elements of G. So let's see. These are all non-zero elements of G, and we've got n of them here. But there are only n minus 1 non-zero elements of G. You know what that means. I smell a pigeonhole principal application. That's what I smell. I smell an application of the pigeonhole principle. At least 2 of the elements from the set 1x, 2x, 3x, nx must be the same element. And remember what the coefficients of x are here. They're numbers from 1 to n. Remember that. two of these elements have to be the same. Oh my goodness. Let's see, do I really want to use I? I'm not sure. I can mistake I for something else. So let me say there exist J and K. And let's see, what can we say about that? J and K are distinct. Kx equals Jx. They're the same element. Yep, that's what it is. Forgive me, I drew a blank for just a second. But that's it. So what does that mean? It means Kx minus Jx is 0, or it means that K minus Jx is equal to 0. Now, we got a problem there somehow. And this is a proof by contradiction, but we want to make the you-know-what hit the fan. Now, K is greater than J, so K minus J is greater than or equal to 1. So K minus J is greater than or equal to 1. Oh, let me just write it up here. K minus J is greater than or equal to 1. Notice also that since J has to be at least equal to 1, K minus J can be at most n minus 1. So we have K minus J is an element of the set of natural numbers from 1 to n minus 1 such that K minus J x is equal to 0. Now, is that a problem? Is that a problem? It's a proof by contradiction. The you-know-what has to hit the fan. We want bad things to happen here. Now, what was it we were trying to prove? Weren't we trying to prove that the order of an element has to be less than or equal to the order of the group? And for the sake of contradiction, didn't we assume that the order of the element x, which is m, is greater than n, the order of the group? And the problem is the order of the element x, that is m, is the smallest natural number that we can multiply x by and get 0. So we have a problem here. K minus j is a natural number less than m. That we can multiply x by and get the identity 0. This contradicts the fact that m is the least natural number that we can multiply x by and get 0. So we got our contradiction. Okay, what do we make of this? The assumption that the order of an element, m, is greater than the order of a group, n, leads to our contradiction. So the assumption has to be false. And that means that the order of an element, m, has to be less than or equal to the order of a group, n.